Hello Year 7. For those of you who don't know me already, my name is Miss Mepham, and what I will be doing is I'll be going through home learning with you. So for this part we'll be doing a PowerPoint presentation, but from next week onwards we'll be using Microsoft Teams to have some live teaching going on. So if we go into our work packs, we will be going through week 8 and all the stuff you'll need to answer the questions and then your Hegarty tasks afterwards. What you will need is you will need a pen, a pencil, a ruler, some paper to work on and your work pack. If you don't have these already, please pause this and get the equipment all ready. So, just like every lesson, we will be starting this with a 5-minute do now activity. So in class, we will usually do this in silence, sit down for 5 minutes and complete as many questions as we can within that time. So what I would like you to do is get a timer or get one of your parents or guardians to time you for 5 minutes so you can work out as many of these questions as possible. I would need you to write down your answers on a piece of paper and show your workings if possible. Now, please start your timer for 5 minutes, pause this video, and then when you are done, we will go on to the next slide. Now that you have timed 5 minutes to complete the Do Now activity, let's go through the answers. Question 1. Convert 2 days into hours. You should have an answer of 48 hours, and this is because if we know that 1 day equals 24 hours, this means we need to double this amount to find out how many hours go into 2 days, and that will mean 48 hours is equal to 2 days. Question 2. What is the HCF of 24 and 60? We should have 12. HCF stands for highest common factor, and a factor is a number that divides exactly into another number and leaves no remainder. If we list out the factors of 24, we should have the following, and if we list out the factors of 60, we should have the following. They are listed in numerical order, which also means from smallest to largest, because now if we want to find the highest common factor, we should be able to see the highest number that appears in both of these lists. There should be 12, so the highest common factor of 24 and 60 is 12. Question 3. Simplify 3k plus 9t plus 4k, take away 7t. We should have 7k plus 2t. If we look at the expression, we have k's and we have t's. From lessons, we should know that we need to collect like terms to be able to simplify an expression, which also means to gather up all of the k's together and to gather up all of the t's together. We can also use commutativity to swap around the 9t and the 4k, and that will mean the same thing in the expression. So now we can see a bit more clearly how many k's we need to add up and how many t's we need to add up. 3k plus 4k equals 7k, and 9t take away 7t is 2t. So we can simplify this to 7k plus 2t. Question 4. Solve 4 plus 6 times 7 minus 9. We should have 37. If we look at what we're trying to solve, we need to look at the operations that are in the question. From BIDMAS, we should know that multiplication comes first, because M comes before A and S, which stands for multiplication, addition, and subtraction. So we should know that this is equal to 4 plus 42, take away 9, and it doesn't matter if you do the addition part first or the subtraction part first, because those operations are equal priority, so we should have the same answer of 37. Question 5. What is the LCM of 6 and 8? We should have 24. LCM stands for lowest common multiple, and multiples refer to the times tables of that number. So if we list out the times tables of 6, we are listing the multiples of 6. So 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, and it goes on and on. And if we want to list the multiples of 8, this is the following list. Now that we have both of these lists, we can see what is the lowest common multiple by identifying what is the smallest multiple, or i.e. the smallest number that appears in both lists. We should be able to see that this is 24, so the lowest common multiple of 6 and 8 is 24. Question 6. Ethan has 5 plant pots. In each pot he plants 44 seeds. How many seeds does he plant? You should have an answer of 220. If there are 5 pots to fill, and Ethan wants to put 44 in each, this means we need to multiply 5 by 44 to see how many seeds in total have been planted. So if we do 5 times 44, that will equal 220, and that means that he has planted 220 seeds. Before we begin, please pause the video, open up your workpacks and turn to page 16 so that we can complete this concept corner together. I'm going to read out the sentences to you, and then I'm going to explain in further detail little bits of information we have learnt in class. Angles formed by a transversal that are in the same region but are on opposite sides of the transversal are called alternate angles. Alternate angles formed in parallel lines are equal in size. In these two diagrams, we can see that we are dealing with two pairs of lines. So this is one pair of lines, and this is another pair of lines. In the first section, we can see that the two lines will intersect at some point, i.e. they will meet. However, we have learnt in class that if they have a triangular sign on the two lines, just like this means that they are parallel and also mean that they will never ever meet. No matter how infinitely long the lines are, there will never be a point where they will touch. We can see that angles A and B are alternate because they are both in the interior region, which is the shaded region in both of these diagrams. And we can see that A is on the left side of the transversal and B is on the right side of the transversal. We can also say that we can form a Z shape like we have done in lessons, and this helps us indicate which angles are alternate. In the second example, we can see that C and D are alternate because C is in the exterior region on the right side of the transversal, and D is on the left side of the transversal in the exterior region too, so this means that they are alternate. However, the important thing to notice here is that C and D are also equal because they are alternate angles and they are formed in parallel lines. And we have discussed in further detail in class that if this is the case, that means that the angles will be equal in measure. Therefore, from what we've discussed, we can deduce that angles A and B are alternate interior angles, angles C and D are alternate exterior angles, and because of the parallel lines in the second part of the diagram, angles C and D are equal in size. Let's have a look at this example. What angle is A alternate to? Now, there is an easy way that we can identify alternate angles in parallel lines. We can highlight the transversal and we can highlight parts of the parallel lines that can make a Z shape. We can highlight where A is, so here, and we need to find the angle that is in the interior region of these two lines, and we need to find that same angle which is in that interior region and is also on the opposite side of the transversal. We should hopefully be able to see that this is D, so we know that A is alternate to D. Here's another example. How many pairs of alternate angles are there in this diagram? Please bear in mind that we are referring to the labelled angles that we can see in this diagram. Let's draw a Z shape again. So, from the previous example, we can see that A and D are alternate. We can also form another Z shape. So, from this we can see another pair of angles that are in the same region and are on opposite sides of the transversal, E and C. So, we should now be able to see that there are two pairs of alternate angles in this diagram. Now that we have gone through the concept corner and two additional examples, I would like you to have a go at these three questions on the paper that you have in front of you. What angle is A alternate to? What angle is B alternate to? And what angles are equal? I would like you to get a timer in time for 5 minutes to answer these three questions on your paper in full sentences if you can. Please pause the video, time 5 minutes, and off you go. Let's go through the answers. What angle is A alternate to? So, what angle is in the interior region and is on the opposite side of the transversal? D. What angle is B alternate to? So, is there an angle in this diagram that is labelled that is in the exterior region and on the opposite side of the transversal? No, so therefore B is alternate to no angles in this diagram. Now, this was a bit of an extension question. What angles are equal? A and D are not equal, and this is because in this example the two lines we're dealing with are not parallel. So, for future reference, and this is very important, most questions we deal with will be within parallel lines. So if there are alternate angles in parallel lines, they will be equal. However, in this example, the lines are not parallel, so the alternate angles A and D are not equal. However, we can say that A and B are equal. And this is because they are vertically opposite, and this is something we have also learnt in previous lessons. So to put that idea into practice, let's look at this example. We want to figure out what is B. We know that angles A and B are alternate because they are both in the interior region but are on opposite sides. So we can easily form a Z shape if you like, and I'll do that for you quickly. Now, we can also say that angles A and B are equal because they are alternate angles within parallel lines. So therefore we can say that B is equal to 50. Now, let's look at a harder example. What if we wanted to find what angles C and D are equal to? First, let's highlight the parallel lines. We can see that angles A and C are equal, and this is because they are alternate angles. If we use our Z shape, and I can do this for you now, we can see that both of these angles are in the interior region and on opposite sides of the transversal. So we can say that C is equal to 70. We can also see that angles B and D are equal because they are alternate angles as well. Let's use a different highlighter. We can see the Z shape here, and we can see as well that they are both in the interior region on opposite sides of the transversal. So we can now say that D is equal to 39. You should now be able to complete page 16 to 17, questions 1 to 4. Please pause the video and take some time out to answer these questions. Before we start this concept corner, please pause the video and turn to page 18 in your workpack. We are going to go through the sentences and the angles within the diagram, and then the further examples that follow this slide will allow you to identify even further how to find corresponding and allied angles. Angles on the same side of the transversal but in different regions are called corresponding angles. Angles on the same side of the transversal and in the same region are called allied angles. Corresponding angles formed in parallel lines are equal in size. Allied angles formed in parallel lines sum to 180 degrees. So from this information we can deduce angles A and B are corresponding angles, angles C and D are allied angles, angles A and B are equal in size, and angles C and D sum to 180 degrees. Here is one example. What two angles are allied? If we think back to the concept corner, we need to find two angles that are on the same side of the transversal, like we can see here A and C are, and we need them to be within the same region. A and C are both within the interior region, so that means that A and C must be allied. Here is another example. What angle is corresponding with D? So let's look and focus on D. For a corresponding angle, it needs to be on the same side of the transversal, so it needs to be on the left side of the transversal, and it needs to be in a different region. So it cannot be in the interior region like E is. That would mean those two are allied, E and D. But the other angle that's corresponding with D needs to be in the exterior region, like B. And just like we've mentioned before, because we can see an upside down F shape as well, we can say that D and B are corresponding. Now that we have recapped what corresponding and allied mean, let's have a go at these questions. What angle is A corresponding with? What angle is B corresponding with? And finally, what angles sum to 180 degrees? What I would like you to do is to time 5 minutes to have a go at these questions on the paper in front of you. Please pause the video, time 5 minutes, and off you go. Let's go through the answers. What angle is A corresponding with? You should have had none. What angle is B corresponding with? You should have D. If we draw an F shape like we have done in lessons, or more so in this case an upside down F, we can indicate that D is in the interior region on the left side of the transversal and B is in the exterior region on the left side of the transversal. So therefore, these two angles are corresponding. What angles sum to 180 degrees? You should definitely not have put A and C. It is really commonly thought that A and C in this example would sum to 180 degrees because they're allied. Yes, they are allied, however, in this example, the two lines we are dealing with are not parallel. So that means A and C will not be able to sum to 180 degrees. However, we can say that C and D sum to 180 degrees, and that is because in previous lessons we know that angles on a straight line always sum to 180 degrees. Let's go through this final example. Here we know that A equals 136 degrees and C equals 82 degrees. However, we do not know what B and D are equal to. So using our knowledge of angles and reasoning skills, we are going to find these values. We can say that angles D and C are corresponding, and that is because they are on the same side of the transversal in different regions. So like we would in class, we would draw an F shape and we can see that C is in the interior region, D is in the exterior region, and they're both on the right side of the transversal. So therefore we can definitely say that they are corresponding angles. What we can also say is angles D and C are equal, and that is because D and C are corresponding angles on parallel lines. This would mean, therefore, that we can definitely say that D is also equal to 82 degrees. Let's figure out B. I'm going to keep the fact that they are parallel lines here by highlighting this in red and keeping it there. I can also use my knowledge of allied angles in this case. It's much easier, understandably, to say that they are corresponding angles in parallel lines, so therefore B is equal to 136. But let me just show you the steps of what it would take to show allied angles. We can label this angle X. X equals 180 take away 136, and we should know this because angles on a straight line sum to 180 degrees. This would mean that X equals 44. We can say that B equals 180 take away 44 because remember, these are in parallel lines, and also angles X and B are allied angles, which means they are both in the same region on different sides of the transversal. Or in simpler terms, we can draw a C shape and we can see that they are both allied angles this way. Just like this. Therefore, we can say that B equals 136 degrees. You should now be able to complete page 18 to 19, questions 1 to 5. Please pause the video and take some time out to complete these questions. Before we go through this section, please pause the video and turn your work pack to page 20. Let's recap rotational symmetry by reading out the concept corner. The order of rotational symmetry is the number of positions a shape can be rotated into and still look the same. The number of times the shape appears the same is called its order of rotational symmetry. All shapes have rotational symmetry of order at least 1. A square has rotational symmetry of order 4. A rectangle has rotational symmetry of order 2. We will particularly be looking at a rectangle's order of rotational symmetry, and this should help to make sense of why a square has rotational symmetry of order 4. Now let's start to look at some examples. On the left we have a rectangle. If we want to see the order of rotational symmetry, we need to think to ourselves, how many times in a full turn can the rectangle fit into itself? Let's have a look. This fits in once and then fits in twice because we need the full turn of 360 degrees to happen, which means that the blue dot comes back to its original spot. So because we saw it fits in twice in that full turn, we have an order of rotational symmetry of 2. Let's look at the triangle. Because this is an equilateral triangle, we should be able to see, even though it's a bit off center in this example, it should be able to show you that this will fit into itself 3 times in a full turn. so therefore the order of rotational symmetry is 3. Now looking at this compound shape here, if we rotate this shape a full turn, let's see how many times it fits into itself. Once, twice, 3 times. So now we can say that this shape has order of rotational symmetry 3. Now that we have defined rotational symmetry, what I would like you to do is look at the 2 shapes that you have in front of you. I want you to write one sentence for each of these questions. What is the order of rotational symmetry for these 2 shapes? Write one sentence to describe how you know this. I'd like you to time 2 minutes to write down 2 sentences on what the rotational symmetry of these shapes are. Pause the video, time 2 minutes, and off you go. Let's have a look. What is the order of rotational symmetry for these 2 shapes? Let's have a look at the L shape first. We should have an answer of 1, and this is because if you turn this shape 360 degrees from its centre of rotation, it only fits into itself once in that whole full turn. So that means the order of rotational symmetry is 1. What about for a circle? We should know now that this is infinite, and this is because no matter how much you turn the shape, it will always fit into itself. Throughout the whole 360-degree turn, the shape fits into itself the whole time, so that means it has an infinite order of rotational symmetry. Let's have a look at a further example. Here we have 4 hexagons that have been divided into 24 equilateral triangles. What you can see here is that each shape has been shaded differently. So the first one not shaded at all, and you can see the sections that have been shaded in the others. If we check the order of rotational symmetry with its different shadings, we'll be able to see that it will be different. So let's look at the first one. 1, 2, 3, 4, 5, 6. So we know that the hexagon that's not shaded at all will have an order of rotational symmetry of 6. Now let's look at the second shape. Once, twice. So now that we have seen in this particular shape how many times it fits into itself, we know if it's shaded like this, this will have an order of rotational symmetry of 2. Here's the third example. 1, 2, 3. So this one has order of rotational symmetry of 3. And finally, for the last shape, this exact pattern only fits into itself once. So that particular shape has an order of rotational symmetry of 1. You should now be able to complete page 20 to 21, questions 1 to 4. Please pause the video and take some time out to complete these questions. Please pause the video and turn to page 22 in your work pack. Let's go through this concept corner. A 2D shape has line symmetry or reflective symmetry if it can be divided into 2 identical halves by drawing a straight line. The diagrams below show shapes with some of their lines of symmetry marked on. Now we're going to look at some further examples to remind ourselves of what line symmetry looks like. Let's look at how many lines of symmetry these shapes have. If we look at the rectangle, it can be folded here and it can be folded here to create 2 exact halves. However, if you try to do this diagonally, the 2 halves would overlap in a very odd way and they wouldn't be identical. So therefore, a rectangle has 2 lines of symmetry. If we look at this particular trapezium, because of the angles within it, we can say that this has 1 line of symmetry. And this is because we will be able to fold this exactly in half and it will be able to fold over. But please bear in mind that this is not the case for all trapeziums. In the third example, there's actually no lines of symmetry. It doesn't matter where you fold it or if you try to fold it with its corners, there will not be two exact same halves if you fold this on top of each other. So therefore a parallelogram has no lines of symmetry. And finally, this cross shape, this has 1 line, 2 lines, 3 lines, and 4 lines of symmetry, because the diagonals allow the shape to be completely identical when you fold this in half too. Let's have a look at the line symmetry in triangles. We have 3 different shapes here, obviously different triangles. What I would like you to do is for each of these triangles, answer the 3 questions that are displayed. What is the name of these triangles? How many lines of symmetry do they have? And explain why. I'd like you to time 5 minutes to answer these 3 questions for these 3 shapes on the paper in front of you. Please pause the video, time 5 minutes, and off you go. Let's go through the answers. The first triangle would be an equilateral triangle, and this is because we know that it has 3 sides that are exactly the same length. So if we think about how many lines of symmetry there are, if we go through each vertex, or i.e. each corner, we can fold the shape in half and it will be exactly the same at 3 points. So therefore there will be 3 lines of symmetry. Question 2. How many lines of symmetry are there going to be in the second shape? Well, firstly, it's called an isosceles triangle, and we should know this because there are 2 sides of it the exact same length. So we should know that from the top vertex, we'll be able to fold the shape in half, and it will have a line of symmetry straight down it. So we can say it will have 1 line of symmetry. Now, the last one would be called a scalene right angle triangle. We can tell it's a right angle triangle because there is a right angle that is highlighted in blue at the bottom left of the shape. But we can also see that the 3 lengths are of different lengths, so therefore it's called scalene. Therefore, there would be no place where the shape can be folded in half and it will divide exactly into 2 halves, so there will be 0 lines of symmetry. In these examples, we will have exactly 1 half of the shape and the line of symmetry, so we'll need to see what the whole shape will look like. So in this example, I've chosen the top length, and you can see that from the line of symmetry on the left, it goes 3 squares across to the left. So in the line of symmetry, you need to do the opposite and draw 3 squares to the right. And then from this, you can see that the line goes down 3 squares, so that forms one other edge of this full shape. And then, in order to finish off the shape, you can draw the remaining line, which is 3 squares away from the line of symmetry. Here's another example. If you choose the top length first, you'll be able to see that you can draw 2 squares to the right, as it reflects the 2 squares drawn to the left. Now, continuing on from this line, the shape goes 2 squares down, so you need to mimic this on the right hand side of the line of symmetry. And then you can see from that last bit of that edge to the edge of the left hand shape, we need to draw a diagonal line so we can finish off the whole shape from the line of symmetry. You should now be able to complete page 22 to 23, questions 1 to 3. Please pause the video and take some time out to answer these questions. Before we continue, please pause the video and turn to page 26 in your workpack. As we have learnt in lessons, the sum of the interior angles in any triangle is equal to 180 degrees. So using the diagram that we have of the triangle, we can say that x plus y plus z equals 180 degrees. Let's go through the bottom example. We can use this fact to find missing angles in triangles. So we can say that x plus 62 plus 37 equals 180. So that will mean if you take away 62 plus 37 from 180, we should have that x equals 81 degrees. We are going to go through 3 examples of where we need to deduce the value of the marked angles. Like the boy in the bottom right of the screen, we need to think about what we know about these angles, and we need to write our reasonings alongside our numerical working out. So through these examples, I'm going to do that. For the first example, we're going to label the marked angle A. Then we can deduce that A plus 33 plus 13 equals 180, because interior angles in a triangle sum to 180 degrees. We can sum the two numbers together, which equal 46, so we can therefore say that A plus 46 equals 180 degrees. In order to find out what A is, we need to subtract 46 from 180, so therefore we know that A equals 134 degrees. For the second example, we are going to mark both of these marked angles B. We can do this because base angles in an isosceles triangle are equal. If you are unfamiliar with this, please think back to the properties of triangles we've learnt earlier in the year. Now we can say that B plus 54 equals 180 degrees, because interior angles in a triangle sum to 180 degrees. If we collect the like terms and we collect the numerical values, we can say that 2b equals 126, so therefore b is 126 divided by 2, which is 63 degrees. Now in this example, we're going to go through C, D and E, which have been labelled accordingly. In the top triangle, we can say that C plus 20 plus 142 equals 180 degrees, and this is again because interior angles in a triangle sum to 180 degrees. We can then say C plus 162 degrees equals 180 degrees. So C is 180, take away 162, and C will then be 18 degrees. Now we can figure out D. D equals 142 degrees, and if we think back to our angle knowledge, we should know that vertically opposite angles are equal, so therefore D would be equal to 142. Now we can finally work out the value of E. 18 plus 142 plus E equals 180 degrees. Because interior angles in a triangle sum to 180 degrees. We can say that 160 plus E equals 180 degrees. E equals 180, take away 160, and therefore E equals 20 degrees. And just to recap, we have figured out all of the marked angles in these 3 examples. Now that we have revised how to calculate interior angles, I would like you to have a go at this larger question. Work out the missing marked angles. Write down your reasons. I would like you to give this diagram some focus. Please sketch this with a pencil and ruler on the paper in front of you. Write in the angles that are already said in this diagram, and then calculate the missing angles accordingly. Do not forget to write your reasons. Please time 5 minutes to do this task, and then once you are done, we'll go through the answers. Sketch, angles, calculations, reasons. Time 5 minutes, pause the video, and off you go. Now, these are the answers you should have had for solving this question after sketching this in your book. The reasons I have written down for this is because you can see that these angles are vertically opposite, and we know that these are equal, so we're able to calculate them. Also, with 81 degrees, we should know that interior angles in a triangle sum to 180 degrees. So if we add 52 and 47 and take that total away from 180, that should leave us with 81. Now, with the others, we should also be able to figure out that interior angles in a triangle sum to 180, so you should therefore be able to figure out the remaining amounts. You should now be able to complete page 26 to 27, questions 1 to 4. Please pause the video and take some time out to answer these questions. Before we continue, please pause the video and turn to page 32 in your work packs. Now, let's recap what we learned about interior angles of quadrilaterals in school. We can use the fact that the interior angles in a triangle sum to 180 degrees, like we've recapped a bit earlier, to deduce that the interior angles in a quadrilateral, i.e. a four-sided polygon, sum to 360 degrees. As you can see here from this diagram, which I will highlight in yellow, we have conjoined two identical triangles together, and then we can see that all the interior angles of the triangle join to make the interior angles of the quadrilateral. So we can see that from each vertex of this new shape, we can see that the interior angles of the triangles are all added together, and therefore we can double this amount to 360 degrees. To put this into practice, we're going to go through 3 examples together. In this, we are required to find the value of A, B, and C, which have been labelled in each of these diagrams. We have a girl at the bottom left saying that she uses bar models to represent each situation, and we have a young boy in the bottom right saying that he formed equations. We are going to go through both of these methods, and you can choose for yourself what is easier to find the missing values of A, B, and C. Let's calculate the value of A. We can say that 100 plus 120 plus 80 plus A equals 360, and this is because interior angles in a quadrilateral, a four-sided shape, sum to 360 degrees. We can add the numbers on the left side of the equation together, so then we can make 300 plus A equals 360. We can also represent this as a bar model. You have a whole bar, and we're going to represent this as 360. We know a section of it is worth 300, and we know the remaining part is A, so we can really visualise the addition that's happening here. From either way, we can deduce that A equals 360 take away 300. That is the subtraction that we can make from the fact family. So then you can say that A is equal to 60, and you have solved this question. Now let's solve the value of B within this kite. We know that 132 plus B plus 40 plus B equals 360. And this is because, again, interior angles in a quadrilateral sum to 360 degrees. We can collect the numbers together, and we can collect the B's together, so we have 172 plus 2B equals 360, because again, we have collected like terms. We can represent this as a bar model as well. So, again, a whole bar will represent 360. We know that we have 172 as a part of this bar model, and we have got 2 parts, and each of those 2 parts is worth B. So now we have got the complete bar model, and we can visualise the addition. So now we can say that 2b equals 360 take away 172, which is equal to 188. And this is because we want to isolate the variable. So we want to get the b's alone on one side of the equation. And then if you know that 2 lots of b is worth 188, to find 1 lot of b, you need to divide 188 by 2. And once you've done that, you should be able to calculate that b equals 94. So you know that b is equal to 94 degrees. And finally, let's figure out what the value of c is. We can see within the circle there is a quadrilateral that we are dealing with. So the main thing that we need to worry about is the angles within this quadrilateral. So, just like before, we can say that 4c plus 3c plus c plus 2c equals 360. And this is because interior angles in a quadrilateral sum to 360. If we do this, we can say that 10c is equal to 360 because we can collect like terms. Just like in the do now, we can collect all of the c's together and we can make it simplified. So now we can say that 10 lots of c is worth 360. We can represent this as a bar model as well. So again, we're going to get the whole bar and represent this as 360. We can say that 4c plus 3c plus 2c plus c in this bar model is equal to 360. And what you should hopefully see as well is that 10 lots of c is equal to 360. So we've got 10 equal parts in the bar model that are worth 360 altogether. So how are we going to calculate c? If we know 10 parts of c equal 360, what is one part of c going to be equal to? We will need to divide 360 by 10 to find the value of c. So that will mean c equals 36, and you have solved this question. Let's have a go at this slightly harder question. Find the value of x. Write down a sentence for each stage of your working. What I would like you to do is to sketch this diagram with a pencil and ruler on the paper in front of you. Remember that you now have some knowledge on how to calculate angles in a quadrilateral, which is again a four-sided shape. Please time 5 minutes to do this task, and once you are done, we can go through the answers. Please pause the video, sketch this diagram, time 5 minutes, and off you go. Let's have a look. If we want to find the value of x, we're going to need to know all of the sizes of the interior angles in the quadrilateral. This is how I started it. I chose the top corner and I said that this interior angle is equal to 60. How do I know this? Angles around a point sum to 360 degrees, and I know the exterior angle around this point is 300 degrees. This will mean that the interior angle is 360 take away 300, which is 60 degrees. I then chose the bottom left angle and I said this would be 19 degrees. And this is again because angles around a point sum to 360 degrees. So 360 take away 341 is 19. Again, with the bottom right corner, I knew that this was 25 degrees because angles around a point sum to 360. Now, what this leaves is what is the remaining interior angle? If I know that interior angles in a quadrilateral sum to 360 degrees, and I can add up 60 and 19 and 25, I can take that total away from 360, which will leave us with 256 degrees, which is the remaining interior angle. Now you can see that 256 and x are the angles around a point, which we know will sum to 360. So therefore, we know x is 104 because angles around a point sum to 360 and 360 take away 256 is 104. You should now be able to complete page 32 to 33, questions 1 to 5. Please pause the video and take some time out to answer these questions. Now that we have completed the learning in the independent tasks, let's do the exit ticket. As with every lesson, we spend 5 minutes at the end in silence to complete 3 questions at the end of the lesson. Please time 5 minutes to complete this exit ticket, and when you have done so, we'll go through the answers. Please pause the video, time 5 minutes, and off you go. Now, for the first question, we should have had 120 degrees for the size of the fourth angle. We should have, for the second question, 3 lines of symmetry, and we should have 20 degrees as the size of angle R. If there are any questions that you are not sure about or need further clarification on, please email me on the email address that is at the start of this video. Now that you have completed this PowerPoint presentation, here is a list of the Heggerty tasks that you need to crack on with, which are due on Monday, and also the optional tasks too. Please don't forget that there are also memory quizzes that should be set by your teacher. And if you've got any questions regarding this lesson, please email me. My email address is on the front of this PowerPoint presentation. And if you've got any queries about the homework, please email your subject teacher that you usually have. Until next week.